Okay, so I'd like to conclude my lecture from yesterday by saying a few words about surgery. So yesterday afternoon you saw a lecture by Bojan Gornik, who defined Dane surgery on a three-manifold. Actually, Zoltan defined it too, didn't he? And so recall what this is. If you have a circle embedded in a three-manifold, and you look at a tubular neighborhood, then you remove this circle, the neighborhood of the circle, and glue it back in by some diffeomorphism of the boundary. And you could call that YC. We can do the same thing in a four-manifold if we have a torus. So if you have a torus embedded in a four-manifold, and it's got a trivial normal bundle, so there's this normal, I should have just written that to begin with, then we can think of this, so and choose a basis for the first homology of the boundary, say alpha, beta, and boundary D2. And then again, glue, form a manifold, say XC, X phi, say, is X minus this neighborhood, and then union a copy of T2 cross D2, glued in by C, which we'll think of as mapping this way. And then X phi is actually determined by phi star of the class of boundary D2. So this tells you which loop on this the boundary 3 torus is dying in the complement. So if we, in terms of a basis, if we wrote phi star boundary D2 is, say, P alpha plus Q beta plus R boundary D2, then we could make the notation more complicated, but perhaps easier to use by writing X phi equals X sub T of PQR. But of course the problem here is you have to keep in mind what basis you're using. Okay, so when you perform such an operation on a fiber of an elliptic surface, it's called the log transform. So let's ask what happens when you look at the K3 surface. The K3 surface is fibered over a two-sphere with fiber of torus. Now, this is not a fiber bundle, right? This has singular fibers. And so we can ask what happens if we do a, say, order P log transform. So it turns out, well, so what is an order P log transform? So choose one of these circles and just leave it alone, and we'll choose, so order P log transform. So it's E2 sub fiber, and now if we choose a basis like this again, it's 0, 1, P. Is it like that? And so what happens when you do this? When you do this, you get a fiber. You'll introduce a multiple fiber. And this multiple fiber so you'll have S1 cross the picture that you have from, a Seifert fibration where you have a multiple fiber. So Cameron called this an exceptional fiber yesterday. You have this, so I'm thinking of, this is closed up. So there's a solid torus, and then your the typical fiber, the generic fiber running around the boundary through the rest of the manifold will cover it P times. And now if P is odd, then one can do a fairly simple calculation to see that this manifold here is actually the simple calculation is that it's homotopy equivalent to the K3 surface. And then it follows from Friedman's theorem that it's homeomorphic to it. But we can calculate its Seiberg-Witten invariant. Remember that the formula read, it's the Seiberg-Witten invariant of the complement times 1 over T minus T inverse, where T stands for the class of the central torus. In this case, the central torus is this multiple fiber. So let's call it F sub P equals multiple fiber. It's kind of backwards language. Actually, the multiple fibers, but anyway, so this is the multiple fiber. And so the generic fiber, the original F, is P times it. So when we include, so now remember, so we have the the complement of this fiber here is just the complement of the fiber in E2. So we're getting the Seiberg-Witten invariant of E2 minus the neighborhood of a fiber, and now included by this map J star, times 1 over T minus T inverse, where T now stands for the multiple fiber. So remember, the Seiberg-Witten invariant of E2 minus a neighborhood was T minus T inverse, but now this T stands for the generic fiber. And since when you include into this manifold, the generic fiber is P times the multiple fiber, we're getting T to the P minus T to the minus P as its image, times 1 over T minus T inverse. So that's the Seiberg-Witten invariant of the log transform. And so if you expand this, you'll get T to the P minus 1 plus T to the P minus 3 and so on down to T to the 3 minus P plus T to the 1 minus P. In particular, each of the Seiberg-Witten invariants of these multiples of the multiple fiber is 1. All the other Seiberg-Witten invariants are 0, and the sum of all the Seiberg-Witten invariants is just the sum of the terms here, which is P. Okay? Okay, so more generally, see, this is a calculation one can make because we're performing surgery or this gluing on a fiber which is homologically essential. This will satisfy, there was a hypothesis in Taub's theorem that there had to be this cohomology class that evaluated non-trivially on the boundary 3 torus. That will happen when your torus is essential. It's important for us to also have a formula for surgery when you're doing surgery on a null homologous torus. And in that case, there's a formula of Morgan, Rufka, Szabo. So this works in general. We don't need essential torus. It says that if you want to do, so this is going to give us a formula for the Seiberg-Witten invariance of x sub t of PQR. Again, we've chosen a basis, some basis for the surgery like this. And now I'm going to have to, unfortunately, write the formula down before I can explain everything in it. So this is some homology class, K of PQR plus multiples of TPQR. So TPQR means the central torus in this after the surgery, this surgery. Okay, I'll explain this class in a second. And you sum this. And this is equal to P times the sum of the Seiberg-Witten invariance of when you do 1, 0, 0 surgery on K 1, 0, 0 plus a certain number of copies of the central torus from that surgery plus Q. I've learned how to list these by using tech. Okay, and one more, R times the sum of the Seiberg-Witten invariance. Now, the one thing that makes using boundary D2 as one of the basis elements is useful because then if I do the surgery that kills boundary D2, I get X back again. So it makes a little bit of the notation simpler, right? Because this is the thing that was already killed in the original manifold. It bounded the normal disk to the torus. So instead of writing x 0, 0, 1, I'll just write x of k plus n t is our original torus. Now, not all these classes necessarily are characteristic. Oh, first I should tell you what these are. So what these are you choose in each of these surgeries, you start with a class k in your original manifold, that's characteristic, and then you choose in each of these surgered manifolds some other class that agrees with it on the whose restriction to the complement is the same. Okay? So that's what these are. And here we're just adding multiples of the central torus. There are many cases where well, first of all, if this torus is primitive, for example, then these integers n are necessarily even in order for this class to still be characteristic. Yeah? If your torus is null homologous, then of course it's 0. So the 0 here, if it's null homologous in any of these manifolds, we can throw away this extra term. There are other times when this sum disappears. But rather than explain that to you now, when I need it, I'll mention it. So sometimes we're lucky and we don't get sums. So this really doesn't give you an exact formula for a Seiberg-Witten invariant of individual elements, but rather for sums of elements, sums of Seiberg-Witten invariants. But you know, if you try sometime, you get what you need. So next, so here's what we've found so far. So here's a formula for Seiberg-Witten invariance for surgery in general. And we use this more particular formula to see that we have, notice, many manifolds here, all different, say for different prime, say different odd p's, these manifolds are all different, these log transforms, because their Seiberg-Witten invariants are diffeomorphism invariants, and the invariant we can use, these are different Seiberg-Witten polynomials, or you can simply say that the sum of the invariants, which is clearly a diffeomorphism invariant, is different for all these different p's. Okay? So this gives infinitely many 4 manifolds, all homeomorphic to the K3 surface, but not diffeomorphic to it. So my next goal is more. We want more. Remember, so our hope is to classify, say, simple hope, classify all 4 manifolds homeomorphic to the K3 surface. And we, at this stage, don't have a prayer. But one way to begin is by constructing a lot of them. So today, my lecture today is supposed to be on not surgery. So this is a technique for constructing new manifolds from old. So first of all, what is it? So suppose you have a 4 manifold containing an embedded torus. So T is an embedded torus of self-intersection 0. And suppose you have some knot, K, in the 3-sphere. So surgery says, remove a neighborhood of this torus, T2 cross D2, and reglue it. Not surgery is, in some sense, a homological version of that. You take the torus and remove it, Take the torus and remove it, and replace it with, instead of another solid torus, replace it with a homology solid torus. So S1 cross a homology circle, and S3 minus the neighborhood of the knot is a homology circle. So there, that's, let's call this X sub K. This, yeah, these are big parentheses. I just want to distinguish them from the other parentheses, make it easier to read. Okay, so and now, of course, there are many ways to glue this, but you want to be careful. You want to glue this in such a way that boundary D2 over on this side, the normal circle to the torus, is identified on this side with point across the longitude to the knot. So the longitude is a loop that bounds a Seifert surface on the other side. So it's a null homologous loop on the other side. Okay. Yeah. So there's another way to write this. So equivalently, you can think of this as a fiber sum. So fiber sum is the kind of operation I was talking about yesterday when we glued together copies of E1 to make En. What you do, so fiber sum just means if you have a torus, then with trivial normal bundle, then you remove the normal bundle of each from 2 such things and glue them together so that normal disk, boundary of normal disk goes to boundary of normal disk. Okay? That's fiber sum, and this manifold here can be thought of as a fiber sum as follows. You take your original manifold X, and you need something to fiber sum it with, and the thing you fiber sum it with is, so let's write MK to mean result of 0 surgery on the knot K contained in S3. So this is the surgery that takes a longitude to the knot and kills it. So that means that it takes a Seifert surface and it caps it off till you get a closed surface in here. Okay? So you take the other manifold that you want to glue it to is S1 cross MK, and the fiber sum identifies the original torus with S1 cross the meridian to the knot. Right? So the meridian to the knot is going to come through and hit each of these surfaces. When you remove the disk that meridian bounds in the new surface, you'll get the ciphered surface in S3 minus the neighborhood of the knot, and that's what you want to glue to the normal disk of T, the boundary of the normal disk of T. So that's another way to write this. Now, so let me give you an illustration of what this does. So here's a picture of the K3 surface. So you've got all these torus fibers that every so often you have say a nodal fiber, and some more these torus fibers and so on. And there are sections. Sections are spheres, so there's this projection into S2. And here, this sphere has self-intersection minus 2. Yeah? And so these guys are tori, this fiber. And what I'd like to do is apply the Injunction inequality to this situation. Now, if I wrote it down correctly, and I kind of worry that I didn't quite, but it's correct in the notes that you'll get later today. The Injunction inequality demands that the surface we apply it to should have genus at least 1. And now, of course, this is genus 0. This is a 2-sphere. But, you know, we can easily make a surface of genus 1 by taking this 2-sphere and some fiber. Right? So then you take these two, they meet in normal crossing, you smooth that out, and you get a torus, sort of what I call a torus section. It's a torus plus, it's a fiber plus the section. It's represented by a torus of square 0. You can check. Square 0, and it intersects every fiber once. Okay? So there's a torus of square 0. So let's, I don't know, let's call it lambda, this homology class. And then so the fiber times lambda is 1. Lambda squared is 0. The fiber squared is 0. So let's apply the Injunction inequality. It says that 2g minus 2, where g is the genus of lambda, that's 1. So that's 0. 2g minus 2 is greater than or equal to lambda squared plus the absolute value of beta times lambda, where beta is any class which has non-trivial Seiberg-Witten invariant. Okay, in particular, suppose beta is m times a fiber, right? Then this is going to be f times lambda is 1, so this is m. So this says 0 is greater than or equal to lambda squared, which is 0, plus m, which is not going to happen very often. So this tells you that in the K3 surface, and this is just part of this sort of exercise that I was talking about yesterday, to see that these other classes in K3, other than 0, can't have non-trivial Seiberg-Witten invariants. So here is, this shows you that m times a fiber can't for any m. Okay? Well, now suppose we do a knot surgery. What happens? So here was, there's our section. Okay, well, here's what we do. We take one of these fibers, say this one here, and we remove a neighborhood. Let's do that. So now I don't have a fibration anymore. So let's forget about the fibration part. I'll remove the neighborhood. And in here I glue S1 cross S3 minus a neighborhood of the knot. And we glue it in such a way that, so these two dots are supposed to indicate the normal circle to the original torus. And here was the original normal disk. And now I've replaced that normal disk by the ciphered surface for the knot. So in here is now a genus G, say, if the knot has genus G. Okay? So now these fibers intersect the surface, but it's not a two-sphere anymore. The surface still has self-intersection minus 2, but now it's a genus G surface. It's bigger. Yeah? So you get let's apply the adjunction inequality to this. It says that 2G minus 2 is, so this time I can apply it to this new, let's call it S prime, is greater than or equal to S prime dot S prime, which now is minus 2. So this time I'm applying it to S prime rather than S prime plus a fiber. I could apply it to S prime plus a fiber as well. Plus, say, let's again think about multiples of a fiber, the absolute value of MF times S prime. So a fiber still intersects S prime once. So this is M, this is minus 2. So it's giving us the possibility that M could be as much as 2G. Okay? So doing this knot surgery is giving us the possibility of having a more interesting Seiberg-Witten invariant. And in fact, that's what happens. So the theorem is, so this is due to Ron Stern and myself, that, okay, so suppose that X is simply connected. And that the complement of a fiber of this torus, so T is again, we're in this knot surgery situation. So we have an embedded torus of square 0 inside of X, K is a knot. And suppose that X is simply connected, the complement of the original torus is simply connected, then XK is homeomorphic to X, and its Seiberg-Witten invariant is the Seiberg-Witten invariant of X multiplied by the symmetrized Alexander polynomial of the knot, where the variable is T squared, where T corresponds to T sub T. So this tells you that at least for as many different knots as have different Alexander polynomials, you get, for example, different K3, different manifolds homeomorphic to the K3 surface. So, for example, if X equals K3, then Seiberg-Witten invariant of XK is the symmetrized Alexander polynomial. Okay, so what I'd hope to do today, and I still do, is to at least give you some ideas on how you prove this. So let's start by talking a little about the Alexander polynomial. So I'm always going to mean this symmetrized Alexander polynomial. So one way to describe the Alexander polynomial is by the Macarena. Does that need a squiggle over the end? So it was a popular dance at the time when we were thinking about this, back in the 40s. So so here's the Macarena for the Alexander polynomial. So if this is K plus, you realize why I call this, it's the out there. So there's a formula for the Alexander polynomial that tells you that, that this Alexander polynomial of k plus is the Alexander polynomial of k minus plus t minus t to the 1/2 minus t to the minus 1/2 times the Alexander polynomial of k0. So that's formula. So maybe you should see how this works. So let's make sure I get the right trefoil things. Okay, so there's a right-handed trefoil, and suppose we want to use this technique to calculate its Alexander polynomial, and let's focus on this crossing there. So here's k plus. K minus is that, which is the unknot. And K0 is, well, it's this thing with this smoothed out, so you get a Hopf link, which it's important to orient. Okay. Now, so this Macarena formula tells you how to calculate the Alexander polynomial provided you have some initial conditions. And the initial conditions are that the Alexander polynomial of the unknot is 1 and the Alexander polynomial of any split link is 0. Okay? So here this is telling you that the Alexander polynomial of the trefoil is 1, because this is an unknot, plus t to the 1/2 minus t to the minus 1/2 times the Alexander polynomial of this Hopf link. So let's finish this by calculating this Alexander polynomial, the link on the right. So let's focus on this crossing here, which it's right-handed. Okay, so let's call this L. This is L plus. Then L minus is completely unlinked. And L0 is well, it's unknotted, whatever the heck it is here. I don't know. Okay, it's unknotted. So this tells us that the Alexander polynomial of this Hopf link is 0, that's split link, plus t to the 1/2 minus t to the minus 1/2 times the Alexander polynomial of the one of the unknot, which is 1. Okay? So this tells us here that for the trefoil we're getting 1 plus t to the 1/2 minus t to the minus 1/2 squared. Okay? Which is t minus 1 plus t inverse, which is the Alexander polynomial of the trefoil. Okay? So here's the idea for the proof of this non surgery theorem. There's this resolution tree that was talked about in the last talk yesterday. And you can always take your knot and make a resolution tree so that every vertex that you see in the tree corresponds either to a knot or a two-component link. And the way you do that is you make sure you only change crossings when you get to a link. When you have a knot, if that's k plus, then k minus is again a knot, and k0 will be a link, two-component link. If you have a link, two-component link, only do the Macarena move on crossings from different components. After all, in the end, you're only trying to make the thing split. So do it on different components, and then L minus will again be a two-component link, and L0 will be a knot. Okay? So that's how you can do that. So so there's one more bit of background we need before we can turn that into a calculation of the Seiberg-Witten invariant. And that background, it has to do with a three-manifold operation, which is due to Brakes and Jim-Hosty. So they call it sewing up link complements. In three manifolds. So suppose you have a two-component link. So you got a three-manifold Y. And in here we have a two-component link. L, so say its components are C1 and C2. And let's let L be the linking number between C1 and C2. I guess we better make this S3. Sorry. There's S3. Here's a two-component link, and let's L be the linking number of C1 and C2. Okay? Okay, so now what you do is you do a sort of HNN thing. You remove tubular neighborhoods of each of these link components and glue their boundaries together to form a new manifold. And of course, there are lots of gluings you can use to do this. So we'll just use these. So let's let S of Ln be glued up link complement where the gluing matrix is the matrix AN, which is, I think it's N. Minus 1, N, 0, 1, where this is the longitude piece. So this is the S1, corresponds to the longitude of the knot, and this is the meridian. Same over here. Okay? And so it turns out if you do this, it's a simple exercise if you use this gluing to calculate the homology of what you get. And the homology is Z plus Z mod 2L minus N. Where, again, L is this linking number between the two components. So what are generating these factors? This Z here, so you've removed two components of a link and you're going to glue them up. So there's going to be some circle that runs around. If you take an arc that runs from one link component to the other, then when you glue up, that'll be a circle in the resultant manifold, and that generates this one. So let's call that the big circle. Generates that. And then a meridian, you've noticed this takes the meridian to the meridian. So the two meridians represent the same element in homology of the glued up manifold. And so the meridian of either component gives you that. Okay, so now here's Jim Hosty's thesis in a nutshell. This is a cool formula. So suppose you have a link and you have two pieces of the link that are running. This has to be an oriented link, by the way. So oriented. So whenever we have links in any of this argument, it turns out it's always important that they should be oriented. So suppose you have two pieces of the link that are running parallel but in opposite directions. Okay? And you want to form this manifold. And so you take this isn't part of the data, but you take a little band between them. Okay? Then Hasti gives a Kirby calculus picture for the resultant manifold. And what that is you split along this band. Once you split the link along this band, this thing here becomes a knot. This is now a knot. It's a single component. And you do zero surgery on this loop that links the band, the original band, and n minus 2L surgery on this knot, and that will give you your sewn up link complement. Okay, so this is Hasti's theorem. You'll see, it's a very useful theorem. Okay, so let me outline. So let's try to outline the proof of this non-surgery theorem. So my goal for these lectures, at least before Friday, is to give 3 different proofs of this theorem. So they're all using very different techniques from 4 manifolds. This proof, however, is the only one that you can dance to. So, okay, so you've got your original knot K, and you look at this, say it's equal to K plus. Oh, I see. So let's call this K plus, K minus, K0, and then of course you build yourself this tree, this resolution tree, and again, each vertex of this resolution tree is supposed to correspond to either a knot or an oriented knot or oriented two-component link. Until at the bottom, what you get is everything is either an unknot or a split link. Okay? And so now the idea is we want to replace each vertex with a 4 manifold. And so in case the vertex is a knot, the vertex corresponds to a knot K, you take and you replace the vertex with xk. Okay? If the vertex corresponds to a link, an oriented link, L, you replace the vertex with x of L, which you define to be equal to x fiber summed with S1 cross the sewn up link complement of L using this gluing matrix A sub 2L. And the gluing takes the torus and identifies it with S1 cross M, where M's a meridian to either link component because they're identified in here. It's okay. And notice that 2L is the surgery that makes the first homology rank 2. This is Z sub 0, so that's Z. Okay? So that's what you do. And now what you hope for is that you can prove some kind of a Macarena formula as you move down the diagram. Okay, so what does this have to do with anything I talked about before? Well, suppose you have so here's a K minus. So I have a left-hand crossing. And I'd like to turn it into a K plus. A K plus is this right-hand crossing. So one way I can do that is to look at, easy to do it, change the crossing. But so the way to do this is to do a surgery, do a +1 surgery on that circle. When you do the +1 surgery, it will precisely change this crossing. Okay? So this thing here, you can write, this is equal to K minus, let's write it as K minus 0, where the 0 means do a 0 surgery, or sorry, +1 means do a +1 surgery on that circle C. Now the thing about C is it's null homologous. C is null homologous. It bounds a punctured torus. And you can see that punctured torus, you know. How do I see this? Here's the punctured torus. There's
Ron, so you say XL equals XT, fiber sum, blah, blah, blah. What is XT?
No, sorry, it's X, and the fiber sum, I'm using this sort of, this is kind of complicated notation, I apologize.
What is X? I mean,
X was the original manifold that contained T, and we're going to do knot surgery on T, replace the neighborhood of T with S1 cross S3 minus a knot complement, and try to calculate the Seiberg-Witten invariant we get in terms of the Seiberg-Witten invariant of X and invariant of the knot. Okay? And what this notation is supposed to mean is, maybe I should do that. It means identify T with S1 cross M. Okay? Okay, so here's the punctured sort of this torus that this C bounds. So here's a disk with, that's twice punctured, and now you take a tube and run it up around the knot, follow the knot for a while, and it comes back this way and finishes up here. So there's a punctured torus. Okay, so C is null homologous. So this, by the way, if Ron Stern talks about what he says he's going to talk about in the last week, he's going to try to convince you that understanding null homologous tori in four manifolds is a good way to think about manifolds that are homeomorphic but not diffeomorphic. Anyway, so when we take S1 cross this gadget, then we have, instead of a null homologous circle, we have a null homologous torus, S1 cross C. Okay? We do one of these surgeries on it, we get K plus. So we have this surgery formula of Morgan-Rufka-Szabo, which we can apply to null homologous tori. And you know, the torus is null homologous in X. This is where the K minus is. It's null in X fiber summed with S1 cross complement, the knot. It's null homologous in K plus still, same argument. So you see that at least two of the three sums in the formula aren't there because the extra term that we're adding on, this n times the central torus, is really 0 in homology. So, and in fact, I just don't have time, I'm sorry, but Andras promises you will have notes today, and I do make the argument in these handwritten notes, that you can see that the Seiberg-Witten invariant of xk plus, that there actually is no sum, and that one can write in general something like this. So this notation is supposed to mean take the torus S1 cross C in xk minus and do a 0 surgery on it. Okay? That's what the Morgan-Rufka-Szabo formula gives you in this case. So okay, so let's try to understand what this zero surgery gives you. So what is xk minus of 0? So that's x fiber summed with a manifold S1 cross y, where y is the 3 manifold that comes from doing zero surgery on this. Okay? And you've done zero surgery on this too, because remember, in order to get x sub k, you take the manifold that you do zero surgery on the knot in S3. That's the manifold M sub k. Okay? So you've already done zero surgery on your original knot. This is the original k minus here. And now you have this new circle C, and you're going to do surgery on that as well. That gives you a manifold Y. Here's the meridian to the original knot. You're going to take S1 cross that and glue it into X along T. Okay, but see, now the point is that if I had better sense, I wouldn't have erased Tosti's theorem, because I want to apply it here. This picture here looks like now notice this guy here is this way, this is going this way. We can put a little band here. And then if we take S, and this is supposed to be 0, if we take S of this guy, 2L, then Jim's formula is, that corresponds to doing zero surgery on a loop that links this band, banding these two together. That gives this, yeah, because notice if I do this, I just get that. And doing surgery on this link now becomes a knot, and we're supposed to do 2n minus 2l, or is it 2l minus n? Surgery, one or the other. It turns out 0 either way. Okay? So that's what this is. So notice that means that this manifold here is just, so this is S of, notice this gadget here, this is just K0. That link is K0. Okay? So this is exactly S of K0 2L. So that's what I meant by X sub L. Okay? So the formula you get, well, it doesn't quite look like the Skane formula you want, because it looks like this. It says that the Seiberg-Witten invariant of xk plus is the Seiberg-Witten invariant of xk minus plus the Seiberg-Witten invariant of xk0, and we're missing the t minus t inverse. Well, t to the 1/2 minus t to the minus 1/2 is the way the formula ran. On the other hand, you can go through the same motions for a link. So what I did is I argued that whenever you have a knot, you have this sort of Macarena formula. And when you have a link, so you can prove, so a link, an oriented two-component, oriented link L, you can prove that the Seiberg-Witten invariant of XL plus, it's basically the same proof, but it's slightly more complicated, is the Seiberg-Witten invariant of XL minus plus t t minus t inverse squared times the Seiberg-Witten invariant of x L0. Where does this come from? So somewhere what has happened is we've found a four-manifold version of sewing up link complements. We've had to cross with S1 and got a link complement that's glued around to itself. We saw that if you have an essential torus and you remove it, the Seiberg-Witten invariant of the complement gets multiplied by t minus t inverse. And now what has happened at this stage, and once again I'm going to get out of it by telling you that it's in the mail, is that we've removed two tori, and we get a t minus t inverse from each one. And then when we glued up, all we did was identify the tori to each other, and that's why these are the same. Okay? So again, you get a formula that's not quite the Skene formula for, oh, I said the bad word, for the Alexander polynomial. So here's what you do to finish the proof. Define some new invariant. Define the invariant theta for knots and oriented two-component links. So for a knot, theta sub k should be the Seiberg-Witten invariant of xk divided by the Seiberg-Witten invariant of x, whatever that turns out to be. And for a link, for an oriented link, L, two-component link L, theta sub L should be the Seiberg-Witten invariant, it should be the Seiberg-Witten invariant of xl divided by the Seiberg-Witten invariant of x times 1 over t minus t inverse. No, 1 over t minus t inverse. Where every time t corresponds to t equals t sub t. T is this S1 cross M, or equivalently the original torus in the four-manifold. So then notice what happens. Then each of these two formulas read the same. So now if you have a knot, this is telling you the first guy here, so divide through by the Seiberg-Witten invariant of x, and you see that it's saying that theta k plus is theta k minus plus, well, now you got a two-component link, so you got t minus t inverse times that theta L, theta k0. Okay? And the same will be true for a link. So the theta of L plus, you can easily check as theta L minus plus t minus t inverse times theta L0. This guy here is a knot now. And so it satisfies the same Macarena relations as the Alexander polynomial, this thing theta. And so what you want to do is check the initial conditions. Well, suppose you have k as the unknot. If k is the unknot, then what do? You remove, so taking S, so what is x sub unknot? It's x minus torus cross d2 union, and you glue in S1 cross S3 minus the unknot. So that's S1 cross D2. Torus cross D2, and you glue it in so that boundary D2 is matched with boundary D2, because that's the Seifert surface. So this is just XBAT. So theta sub unknot is 1. Okay? And for a split link, I have to rely on a fact from Seiberg-Witten theory that I haven't told you yet, but sorry. So what is theta sub split? Well, if you have a split link, then inside of this sewn up link complement, there's a two-sphere that separates them. That's essential. In S1 cross it, you'll get a two-sphere of square 0 that's essential. And a basic fact about Seiberg-Witten invariance is that if you have a manifold that contains an essential two-sphere of square 0, then the Seiberg-Witten invariants vanish. So this tells you that theta sub split is 0. So this tells you that theta is nothing more than the Alexander polynomial of k. Well, not quite. Notice here we have t minus t inverse instead of t to the 1/2 minus t to the minus 1/2. So that says instead of calculating using the variable t, you're using the variable t squared. So that is sort of a proof of why this not surgery theorem works. Okay, thanks for your attention.